You ever wonder how we can see the invisible forces that shape our entire world? Things like magnetism, electricity. They're everywhere, but they're totally abstract. Well, it turns out the way we learn about them, the way we experience them, is going through a massive revolution.
Okay, let's just get right into it. This has always been the big problem in physics, right? How do you take a concept like an electrical field and make it something you can actually feel, something you can really wrap your head around? For a long, long time, the answer looked like this thing on the left, a really complicated hand-drawn diagram trying to capture just one static moment. But today it looks like the graph on the right. Perfect, clean, dynamic, and generated in the blink of an eye. This shift from static pictures to live data is exactly what we're going to explore. And our guide for this whole thing is its source material, a lab manual called Experiments and Demonstrations in Physics. You can think of it as a field guide to this incredible new world of hands-on, high-tech science. So, what's really driving this huge change? Well, it all boils down to one core innovation, the rise of computer-assisted discovery right there in the lab. The real hero of this story is something called a data acquisition system. Think of it like a universal translator for the physical world. It uses all these specialized sensors to take stuff like force or temperature or voltage, and it instantly turns it into digital data you can see and play with. And this just shows you how ridiculously simple it's become. You connect a sensor, you run your experiment, maybe you drop a magnet through a coil or something, and bam, you immediately see the physics behind it all, graphed out right in front of you. No more tedious calculations, just instant insight. But it's not just about seeing the data. The software that goes with these systems is an absolute beast. You've got real-time graphing, data smoothing to get rid of the noise, and here's the really cool part, over 20 built-in functions to fit mathematical curves to your data. So you're not just observing, you're analyzing and proving physical laws on the fly. So, with all these tools, we can do something truly remarkable. We can recreate the most important experiments in the history of science. And stuff that took years of painstaking work, now it takes just a few seconds. Take Hans Christian Ørsted. It's 1820, he's in the middle of a lecture, and he gets this sudden idea to put a wire carrying an electric current next to a compass needle. And just like the manual says, a pronounced deflection was observed. In that one single moment, the fundamental link between electricity and magnetism was discovered. Now think about that. That same world-changing discovery, the one that totally reshaped our understanding of the universe, can now be demonstrated and graphed in the time it takes to flip a switch. That's just astonishing. Or how about Heinrich Lenz? Back in 1831, he's the one who figured out that when you move a conductor through a magnetic field, it creates a new current, and that current makes its own magnetic force that actually opposes the original motion. This is the whole idea behind magnetic braking. This invisible hand of magnetic braking, it used to be just a theory you'd read about, but now you can literally watch it happen. You can see the motion of a pendulum die out on a graph the second a magnet gets close. The abstract becomes completely, totally concrete. And that's really the key here. This technology isn't just about recreating history. It's about visualizing the fundamental laws of the universe that are normally completely hidden from us. So, for example, on the one hand, you've got Ampere's law. Looks kind of intimidating, right? All those symbols. But on the other hand, you have this, a perfectly straight line on a graph that proves the exact same thing, measured instantly. Which one gives you that aha moment, that gut-level understanding? For most of us, it's definitely the graph. And here's where it gets really fun. You can deconstruct things. I mean, a simple, clean wave is one thing, but a more complex square wave like this one is actually built from a bunch of different frequencies, all layered on top of each other. With these new tools, you can instantly break that complex wave down into all of its fundamental ingredients. It's like seeing the unique spectral fingerprint of a signal. And this tech doesn't just make old ideas easier to get. It actually brings some of the greatest scientific achievements of the 20th century, discoveries that literally won Nobel Prizes, out of the world's most advanced labs, and puts them right into the classroom. Just think about this for a second. J.J. Thomson's discovery of the electron, the invention of the transistor, which basically powers our entire modern world, the insane breakthrough of high-temperature superconductivity. These aren't just history lessons anymore. They are now actual hands-on experiments for students.
When J.J. Thomson won the Nobel Prize in 1906, they told him he was worthily treading in the footsteps of your great and renowned compatriots, Faraday and Maxwell. He was joining this incredible lineage of discovery.
And Thomson's work led to the measurement of this number, the charge-to-mass ratio of the electron. This isn't just some random number. It's a fundamental constant of our universe. It's one of the core values that helps define reality itself.
But here is the most important part. This is no longer just a number you have to memorize from a textbook. As the source manual shows, students can now use modern versions of Thomson's own experiment to measure this constant for themselves. They are literally treading in those same footsteps.
This quote just captures the feeling perfectly. When the inventors of the transistor won their Nobel, the presenter talked about the supreme joy that comes from seeing breathtaking vistas from the summit unfold. That feeling of genuine discovery, that's exactly what this technology unlocks. So when you boil it all down, the mission here is pretty simple. It's about turning abstract physical theory into tangible, hands-on discovery. It's about empowering the next generation by giving them the tools to not just learn about science, but to actually do science. Which, of course, leaves us with one final and very exciting thought. What will the next generation be able to discover when the greatest experiments in scientific history are available right at their fingertips?